Good afternoon.
Good afternoon.
All right, let's see. Who are we missing in Mogyan? Oh, I guess everybody's there. Everybody's there in Winslow and St. John's. All right, awesome. All right, so today we are in middle of practice 1 on 4.5. And so the hope is that we'll finish 4.5, maybe go on to 4.6. I'm not sure. We'll just see how that goes. So that's kind of our plan. Does anyone have any questions, comments, concerns before we get started? Okay, so just to let you know, I would say there's probably a 50-50 chance that we'll have one day next week as a Moodle day. It just sort of depends on how the flow of the week goes, and I've got some things going on that I might have to go. So I'll just kind of we're just gonna see how do what we can Monday and Tuesday, and then some things might happen. I don't know. We'll just have to wait and see. So, but I just want to let you know the week might be a little weird next week. So, we'll see. Okay. All right. Well, let's go ahead and get started here. We're, like I said, we were in the middle of practice 1, and we had got to the point where we were doing the volume of this open top box. And these were the dimensions that we came up with. And I was curious to see if you could take the derivative of this. And so, so let me just pick somebody at random and let's see how far we got on the derivative. All right, Joey, how do you do the derivative of something like that? This.
Okay, I just realized that I did it wrong, so give me 1 second.
Okay. All right.
I got 2x, but I know that's not right. So
Okay, so let's go through it here. So to do this derivative, what I would do is use the product rule. And so you take the first, so think of 12 minus 2x squared as your u and x is your v. And so you take the first 12 minus 2x squared times the derivative of x, which is 1, plus then the derivative of 12 minus 2x squared. You bring the 2 in front, and it's 12 minus 2x to the first. And then the chain rule says you got to multiply by the derivative of the inside part, which is negative 2, and then times the x. Okay, so this part in red here, I'm using the chain rule. So any questions on the derivative? All right, so let's simplify this. All right, so since this is just to the first power, I could go ahead and square this out. And I get 144 minus 2 times 12 is negative 24. Double that, negative 48x plus 4x squared. And then distribute the negative 2x and the 2. So negative 4x times 12 is negative 48x times negative 2x is 8x squared. Now, if this wasn't to the first power, you couldn't multiply through like that. Then combining like terms here, I get 12x squared minus 96x plus 144. Okay? So, any questions on the derivative? Okay, now the max and the mins occur where the derivative is 0 or undefined. This is a polynomial. It's always defined. So really what we need to worry about here to get the max and min volume, in this case we want the max volume, is we've got the derivative, set it equal to 0 and solve. Okay? So now it's just an algebra problem. So the first thing I would do is divide each thing by 12 and then solve it. Okay, so I'll let you see if you can finish it out from here. All right, so Jordan, when you solve this for x, what do you get?
So x is equal to 2 and 6.
Okay, now one of those answers you're going to throw away. Which one and why?
Would it be 6? Because in your original equation, that's going to make it be 0, right?
Yep. So see if you're cutting off, from your piece of tin or whatever, the x by x corners. Well, if there's 6 by 6, you'll have no volume. So that in fact will give you the minimum volume, 0. Okay. So throw that answer away. We don't want 0 volume. What we're trying to figure out is the maximum volume. All right. So if, let's see, Jordan, your other answer was what, 2? Is that what you said?
Yes, 2.
Okay. So then if x is 2, then what are the dimensions of the box? Okay. So everybody figure out the dimensions of the box now. If x is 2. Let's see, Rhett, were you here yesterday? No? Okay. So let me see if I can help you understand what's going on here. Okay, see we had this 12 by 12 piece of tin, and so we cut off these little X by X corners and then folded them up to make like a little brownie pan. Okay? So if these sides were originally 12 by 12 and we cut off little 2 by 2 corners, then what would be the length and the width of the pan? Or the box? So if X is 2 in the figure, then when we fold it up, what's the length and the width here going to be?
Are you asking me?
Yeah.
Oh, 8. Sorry.
8. So they're both going to be 8. And then what's going to be the height of that pan, Brett?
2.
2. So the dimensions will be 8 by 8 by 2. And so that will be the maximum, that will produce the maximum volume, okay, for that, from that piece of tin, okay? All right, any questions on that? So the idea is this. So if I were to graph the volume function, so when X is 2, that produces the maximum volume. When X is 6, that produces the minimum volume of 0. So when we optimize something, we're trying to maximize or minimize something. And so it occurs when the derivative is 0 or undefined. Now, in these real life situations, usually it's when the derivative is 0. Okay. All right, so let's go through this. So solving optimization problems, okay? I would just, if I were you, I'd just write down the part I've highlighted here. Okay, so step 1, read the problem. Now, you read it until you got to make sure that you can find out what formula that you need, because you have to take the derivative of that formula. So you've got to read it and be thinking, okay, what's the formula here? All right, next, draw a picture. Now, you don't have to draw the picture, but sometimes when you draw something like the box, then you're like, oh, okay, I know the formula for that. And so that can be helpful. Number 3, introduce variables. All right, so, okay, so I shouldn't tell on any classes, but my morning class when we were doing some of these problems, and I was having students work through some, it was funny to me how I have this one student that wants to introduce new variables. It's like if X is the length, then 2 times the length, instead of being 2X, she would want to make that Y. And anyway, she had like 3 extra variables. And you want to try to minimize the variables. All right, write an equation for the unknown quantity. And this is where it really helps to practice on these problems. Oh, speaking of which, on the student success organizer, where it has problems, suggested problems, 1 to 57 every other odd. Okay, don't try number 25. Okay, if you're going to try some of those, I would recommend it, but 25 is just ridiculous. Okay. Okay, so let's see what else. Test the critical points and the endpoints in the domain of the unknown. Basically, you're just checking to see if it makes sense. So, like in the last one, cutting off a 6 by 6 square didn't make sense. You're not going to get a maximum volume that way. Okay, so that's just sort of the general thing. But as far as the math goes, we've actually done the calculus already for this section. It's just pretty much take the derivative, set it equal to 0. I mean, that's the big idea. All right. So next, example from business and industry. When asked to minimize material used, it is customary to ignore the material's thickness and the waste in manufacturing. You minimize the surface area. And so when you're trying to minimize material, you usually find the formula for the surface area of the object and minimize that. Okay? All right, so whoops, okay. All right, you've been asked to design a 1-liter can shaped like a right circular cylinder. To minimize the material used, what formula must we use? Okay, maybe you saw it already. But what's the formula for surface area of a right circular cylinder? And feel free to use the front flap of your book if you don't know, or maybe we can just sort of piece it together. Well, what would be the area of the top and the bottom of the can?
So it would be 2 pi r, and then you do it by height, right?
Okay, so 2 pi r h.
Oh yeah, r.
So
yeah.
that's the area on the around the can. So like the label. Okay? And so what about the top and the bottom? What would be those areas?
You would add that to the area of the top and bottom.
And so, what's the formula for the area of the top and bottom of a can?
R squared.
Pi r squared.
Pi r squared. And so you got 2 of those, okay? So 2 pi r squared, so this is the top and the bottom of the can. 2 pi r h, that's the area around the can, okay? So that would be the formula if we want to minimize the material. That's the formula that we would use. Okay. Now this is a true story. All right. So my wife's adopted cousin, he ended up getting a PhD and got over $1 million in royalties by designing a new can. And was just perplexed. But he was an engineering student, and anyway, it's just amazing to me how much money is in that. But when you go into engineering, so much of what you do is trying to maximize or minimize things. And I really don't know what he did. I guess I should have found out, but I do know that back in the day, cans used to not stack very well, and now they do. So I don't know, maybe he came up with that. But anyway, okay. So let's actually go through the process here. Okay. So it says design a 1-liter can shaped like a right circular cylinder. What dimensions use the least material? Okay. So one of the things that we're going to need to use is, well, let's go back to the formula. Okay, we have a little bit of a problem here, in that when we take the derivative, I mean, over here on the left we have s prime, but here it's like we have kind of too many variables. And because we're not taking the derivative with respect to time like we do with the related rates, so what we need is a way to write the radius in terms of the height of a can. Okay, and so to do that, we're going to use the fact that its volume is 1 liter. Now, to make our life a little bit easier, it sounds weird to say it that way, but we're going to think of a 1 liter as 1,000 cubic centimeters. Because see, our dimensions are all going to be in centimeters. Okay? So instead of having a fraction of a liter, we're going to just use 1,000 cubic centimeters. All right? So the formula for volume of a can is pi r squared times h. So if I plug in 1,000 for V and divide by pi r squared, then I get h in terms of the radius. So what that allows me to do is substitute in so that when I take the derivative, I'm only going to have to deal with one variable. So in place of, so I have 2 pi, the surface area is 2 pi r squared plus 2 pi r, and in place of h, I'm going to substitute in 1,000 over pi r squared. All right, and now the pi's cancel, and then r's cancel, and so I'm going to get 2 pi r squared plus 2,000 r to the minus 1. So now I have s in terms of just one variable. Okay. So now what I would like you to do is I would like you to take the derivative here, set it equal to 0, and solve for r. All right, so Rhett, what did you get for s prime?
4 pi r minus 2,000 r to negative 2.
That is correct. All right, so Nathan, when you set that equal to 0 and solve, tell me what you get for r. Now there's some tricky algebra here, so if you get stuck, don't hesitate to ask me for help.
Okay, I got it to pi r minus 500 over r squared.
Okay. So basically, at this point, you divided everything by 4. Okay. So that would work. Okay. So here's what you do at this point. There's actually 2 different approaches for algebra that you could work here. Okay. One is you could multiply everything through by the least common denominator, r squared, to clear your fractions. But I never like multiplying variables by 0. Okay. So what I would recommend you do is move this 2,000 over r squared over to the other side. And then think of it as like a proportion. So you could do the same thing. You've already just multiplied by 4, or divided by 4. But go ahead now and cross multiply and then solve for r. All right, so tell me what you get.
The cube root of 500 over pi.
Okay, so go ahead and put that in, because chances are you're going to have to put that as a decimal.
$5.419.
Okay, when you did your division, so you did the cube root of 500 divided
Over
by
pi.
500 over pi. Did you put the pi underneath the radical as well? So
No,
yeah, it's got to be under the radical as well when you do the cube root. Oh wait, you said 5.419 when you do the cube root. I think you did it right. Isn't this what you said?
Yes.
Yeah.
Yeah, I'm sorry. You did have it under the radical. Okay. Okay, so that's the radius. Now the other dimension that we need is the height. So to get the height, what we do is we plug that into this. So we've already solved for r. So now we do 100 divided by pi r squared, plug in that value for r, and then figure out what the height is. All right, so David, when you've got the height, let us know. So 1,000 over pi times what we got for r squared.
$10.839.
There it is. Okay. And so actually it ends up being double. I mean, the reason why it's not double exactly 2r is because of rounding. Okay. All right, any questions on that? So this graph is the surface area. So how much material is used? And so we're keeping the volume constant. And so what we're doing is we're trying to figure out this point that would minimize the material. And so again, that occurs when you take the derivative, set it equal to 0, because we have a horizontal tangent here at the minimum. All right. So it says, so next, in order to take advantage of mathematical properties, it is often advantageous to draw the figure on a coordinate plane. Now, I've learned that, this isn't just in calculus, but a lot of times I've seen problems like on the ACT or different standardized tests where if you're trying to find a radius or something, you put it on a coordinate plane, and then you can use the distance formula, you could use the midpoint formula. There's a lot of things that the coordinate plane does for us. All right. So it says we are to find the largest area of a rectangle to be inscribed in a semicircle with radius 2. Draw the picture. All right. Well, I kind of messed up there. But inscribed means the rectangle touches all the parts of the semicircle. Okay? So you have the semicircle, the rectangle touches all the parts of the semicircle, and then the radius of the semicircle is 2. So it's the distance from the center of the circle to the edge. But see, here's the point, is that if you asked me to do this problem cold, and I didn't think about the coordinate axis, I probably would look at this and say, there is not enough information. The largest area of the rectangle, how can I know the area of a rectangle is length times width, but I have no information about that. And so I would look at that and how could you do that? All right. But now watch what happens when all of a sudden I put it on a coordinate system. When I put it on a coordinate axis, then all of a sudden I see, okay, so if this radius is 2, then the radius out here, the diagonal of the box is 2. And then this forms a right triangle. Okay, so once you start, and then you have the equation of a circle, and then you can start writing any point or the length and the width in terms of just x, because we know that any xy point lies on the circle. And so if we know that x squared plus y squared equals y, and I solve that for y, I get y equals plus or minus the square root of 4 minus x squared. Well, I know the positive part is this upper semicircle. The negative is the lower semicircle. And so by putting it on that coordinate axis, all of a sudden we see relationships that we don't see without it. Or at least that's how it works for me. Okay, so now we have the area of this rectangle is length times width. So this length is x. This length here, if we go x in this direction, its length is still x. So it's the area of this rectangle is 2x times y. But now in place of y, I'm going to substitute radical 4 minus x squared, because I know that that's the relationship that x and y have because they lie on this circle. So then the formula becomes, well, let's see. So 2x So 2x, and then in place of y, I put radical 4 minus x squared. So that's like the width. So the length times the width. All right, so let's have you do the calculus now. So now to maximize this area, we're going to take the derivative and set it equal to 0. So go ahead and do that. All right, so Nathan, when you've got the derivative, let us know. All right, you got it? Or I just want the derivative. You don't have to solve it yet.
So I didn't get time to like make it small, but lengthwise I got 2 times 4x minus x squared to the 1/2 plus 2x times 1/2 times 4x minus 2 to the negative 1/2 time minus 2x.
Okay. All right, so mine's just in the opposite order, but that's okay. It doesn't matter. Okay? So 2 times 4 minus x squared to the 1/2 plus 2x times 1/2, 4 minus x squared to the negative 1/2 times negative 2x. Okay, now if we do clean that up, the 2 and the 1/2 will cancel. So you have x times negative 2x, or the 2 and the 1/2 cancel. So x times negative 2x is negative 2x squared. And then I went ahead and put this as a radical in the denominator, plus 2 times the radical 4 minus x squared. Now, once again, the algebra trick is similar to the last algebra trick. To set this equal to 0 and solve it, what you do is you move one of these terms over. I would move the negative one over to the other side and then cross multiply. Okay, so I'll let you go ahead and do that to solve for x. All right, so Rhett, when you've got it.
I'm really confused, but I got 8x to the 4th. I don't know if that's right.
Well, when you cross multiply, you get 2x squared times 1, and then the radicals are going to just come out of the radical, because radical times itself, so you just have 2 times 4 minus x squared. All right, and then when you combine like terms, you move the 2x squared, and you just add the coefficients. You don't mess with the exponents. So it's going to be 4x squared equals 8. Divide each side by 4. X squared equals 2. So x equals plus or minus 2. And since x represents the length of part of your rectangle, you just use the positive value. But because what x represents is this distance right here, the full distance is actually 2 radical 2, because it's radical 2 in this direction, radical 2 in this direction. So that whole length of the rectangle is 2 radical 2. Okay? So that's the length, 2 times radical 2. So what would the width be? If we plug in radical 2 for x, what do we get?
Radical 2.
Radical 2. So then the dimensions of the rectangle then would be 2 radical 2 by radical 2. And that would give us the maximum area. All right, any questions on that? All right. So part 4, you can we're gonna skip that. So you can just draw a line through that. It is kind of interesting that like the speed of light isn't always the fastest between in straight point, because when it goes through a medium like water, light actually slows down. And so if you can bend light, sometimes it's actually faster. And there's some problems that are similar to that, like if you were pumping oil through underneath the water, it actually costs more to build a pipeline underwater. And so even though the pipeline might be longer over land, you know, it might actually be cheaper. So anyway. Okay, let's go to part 5, an example from economics. So at a production level yielding maximum profit, the marginal revenue is equal to the marginal cost. So remember, the marginal means take the derivative. So the marginal revenue would be R prime. The marginal cost is C prime. So when you have a maximum profit, that means the change in profit would be 0. You've already maxed out. So if P prime is 0, then that means P prime is R prime minus C prime. So if the marginal profit is 0, you're already at the max profit. All right, so let's just set up practice 5, and then I want you to I want you to solve it. Okay, so if whatever we don't finish, I want you to finish this problem before class Monday. So suppose that R of x equals 9x. That's the revenue function. C of x equals x cubed minus 6x squared plus 15x, where x represents thousands of units. What equation should be used to find the production level that maximizes profit? So can anyone tell me the equation that I'm going to solve?
Would it be P equals R minus C?
Well, that would be the profit. That would tell us what the profit is. I want to maximize the profit. So what I want to do is have R prime equal to C prime. So what's the derivative of R?
9.
9. What's the derivative of C?
3x squared minus 12x plus 15.
Yeah, plus 15. So you set those equal to each other and then solve it. Okay? So see if you can solve it for x. And remember that your answer is going to be in thousands. So you've got to put the final answer in thousands. Okay, so we'll kind of pick it up from there on Monday, because